I'd like to thank the organizers. It's been a nice conference so far, and I expect it will definitely continue. I think some people noticed there are 33 slides. I have lots of pictures. So first, we'll start off with some non-pictures. I'm looking at floating drops, and I would like to show that under some circumstances, these things are symmetric. And so just to begin, I'm going to give you a whirlwind tour of classical solutions to capillary surface problems. These things are mean curvature is proportional to height. This constant of proportionality is kappa. And I could maybe skip the explanation of what kappa really is, except it'll come up in the physics of my problem. And so it's the density, or maybe even the change in density between two fluids, times the gravitational constant. If you'd like, it could be 0, then you get constant mean curvature surface, and divided by the surface tension. All of this comes from some variational arguments, and well, that's the capillary surfaces. So maybe going back to Da Vinci, I think he was the first person to care about what happens when you put a little straw into a container and watch the fluid rise. He didn't get very far with it. We've had a lot of progress in the last, say, 50, 60 years or so with such things. Okay. You'll have some Neumann-type boundary conditions on the end. If you put a little drop of fluid on a surface here, and I don't think I want to do that with all the hardware up here, but okay, it does not have to remain a graph. It can curl over. This is a Cecil drop. So you can also have water, say, condense on the ceiling or hang from the spout of your sink, okay? And you'll have a pendant drop in this case. And really, this is saying that the density of the fluid is bigger than what's below, and this thing will have some inflection points. These things do not need to be stable, okay? And this is an example of something that would appear hanging from your sink for a very, very short period of time. One of the things that I'm going to rely on a bit, all of these will be component surfaces in my floating drops. And so the results I have involve an unbounded region, say all of R3. And that's not a very physical setup. So it just so happens that this is something that's been heavily studied. If you take a hockey puck, say, and dip it into an unbounded bath of fluid and pick it up very slowly, you can get something like this. And I don't know if you guys can see the dotted line here that's the reference fluid, okay? And you just pull this up very slowly. This is an unbounded liquid bridge. This is something that I've spent some time in, and well, we probably won't have enough time at the end to talk about other possibilities, but if you have an annular capillary surface, that would be what would happen between the straw and the edge of your glass. Okay? For whatever reason, this hasn't been as heavily studied. I think I'm the world's leading expert on this with 2 papers. So here is a floating drop, and I'll come back to this picture here in a minute. You have 3 different densities. You have air, say oil, and water below. And then I'm going to give these surfaces a name. U is this upper surface, V is the one below, and W is this exterior surface, and this picture, for whatever reason, is truncated a little bit close in. Now you might just look at this little kind of force balance diagram. I'll come back to this after I've explained it some more. Okay. We have these 3 interfaces. Sometimes we will give them a label S01, S02, and S12, okay? But basically you just have these 3 fluids, right? And we're going to, at least for the purposes of this paper, this result, assume that these things are smooth, C2, all right? And that they meet at what I will call the free boundary, which is just a smooth closed curve, right? The regularity of that free boundary is an open problem at this point. So this slide's a lot of physics in the way of looking at it. You have some surface tensions, sigma 0, 1, and so on. And these things are all non-negative. And they need to, actually they should all be positive. and they need to satisfy some force balance relation. And the force balance relation just goes back to this picture, which will appear again here in a moment, that says that you can't have one direction pull too much, because we're assuming that this is in equilibrium. Okay. Then you have some contact angles. The contact angles satisfy this Neumann triangle relation. There's really not a whole lot to say about that. Okay. If you look here again, if this, say, this surface tension was much larger, then this wouldn't be in equilibrium and it would want to pull in that direction. Okay. So back to some equations. When you set this thing up, each difference in density can be represented by different capillary constants. And you notice that I could have, say, the fluid drop be heavier than the supporting fluid, in which case this capillary constant would be negative, and it would go to the pendant drops that you saw. And each of these things must satisfy some sort of mean curvature equation where the kappas would be one of these three things. There's a Lagrange multiplier in each of these, and you just kind of have to bear with it as it goes along. Okay. So I'm going to show you a theorem about the symmetry of this if it's in all of R3. And I had to make an assumption in order to show this. And so these next three slides are explaining what I'm calling the division property. And so you see you have a floating drop. And then what I'm going to do is say that in some sense, at least, the free boundary is flat. So this first slide is saying that the free boundary is completely contained in this horizontal plane. Okay? And that, in fact, there does exist such a horizontal plane that picks up the entire free boundary. And then the next two slides are actually very similar. The other possibilities are that this plane could pick up not only the free boundary, but the entire part of, say, the upper surface here. Okay? And then through the magic of a minus sign, it could also pick up the entire interface between the drop and the supporting fluid. Okay? And if you assume that one of these three conditions holds, then we have this division property. All right? Just saying that there is a plane such that somehow it picks up the free boundary and it might pick up a little bit more. And if you assume the division property and you have a partition of the whole space and the drop itself is bounded, then, well, the equations that we had talked about the mean curvature of these different surfaces, and if they only depend on the height, which these do, this theorem is slightly more general than the physical thing that I need. And then there's some decay on this exterior surface. And if you have these things, then the drop is symmetric about some vertical line. So I'm going to give you a little sketch, but maybe first I'll explain. Henry Wente proved some results if you're just talking about sessile drops or pendant drops. And a portion of this leans on that. Uses this idea of Alexandrov moving planes. So if you would like to take a short nap, we had an excellent 2-second or maybe 1 minute overview of the next part. And this relies on maximum principle type arguments, basically due to Hopf and Sarin. Then the exterior part is the part that I didn't know how to do until recently. And I saw a talk that Bob Finn gave at Kansas State when he was looking at what you do if you rest a little solid object, like a little floating body. Okay? And he was worried about existence problems, but for whatever reason, one of his proofs was very useful to me. And his work is with Tom Vogel, and then Tom Vogel is the one who studied these unbounded liquid bridges. Okay. So the idea behind these Alexandrov moving plane arguments, okay, which we will use just for the drop itself. We'll worry about the exterior surface later. You take some vertical plane that's just a mathematical construction. It doesn't disturb the fluids. Okay? And then you move this plane into the drop. So T is a one-parameter family of these planes. And then once you start cutting into the drop, you start reflecting. So the things with the primes involve reflections of these surfaces about that plane. And then once you're through that, okay, you have this. So maybe let me not worry about this notation too much. Here's the picture. I'm moving the plane. This is a horizontal slice. I'm just chopping a horizontal slice, and you move this plane through, and then you have to stop at some point, and you stop when it touches, is one of two geometric ideas about when to stop. And then the other one is you move this plane until the normal becomes parallel to the plane. So the normal would be contained right in there. Okay? And if you hit that, then you can stop. All right, so here you go. This is the heart of my paper, and it's a mess. Right? There are lots of different cases. Okay? The reason that there are a lot of different cases, and the whole reason for my hypothesis of having some horizontal plane, okay, the division property, is because when you start reflecting things, you're worried about what surface touches what other surface. Does it happen up top, or does it happen below? Do you have these things where, you know, all the action is on the free boundary? Okay, and it's a bit complicated. Let's look at the most complicated of these and see if we can, you know, make some little bit of progress there. So what this is saying is, basically it's the second picture, and I'll show it again, okay, here in a moment. If you're looking on the free boundary, you're trapped in this plane from the division property, and at some point, okay, you're in the division property plane, and you're pushing the reflecting plane through, and at some point the normal becomes parallel. Okay? It's this picture here, where S in this case is just the curve of the free boundary. And you have this prescribed mean curvature equation, and here I'm not assuming that anything is really a graph, it just depends on the height also. And we have this proposition that, loosely speaking, falls in Henry Wente's paper, but this is really, the heart of it is due to Treinen. Okay? And it's a typical maximum principle type idea where you have a point, this time it's in the boundary, and you have solutions to the equation. Okay? The two solutions are equal, then you have an inequality. Okay? You have an inequality. And then, well, since it's on the boundary, you need to have, say, something about the tangential directions, the first derivative in any non-tangential direction. Then you also need the second partial derivatives to be equal. And if these things are true, then the surfaces are the same, and the picture you just saw is absurd, right? And so let me just, for just a moment, tell you that this condition here follows basically from the idea that you're reflecting, and this condition here follows from looking at the physics of what's going on, okay? The other two things, and I'll just flash this for a second, this is just your basic, you know, EHOP maximum principle, and then this is the one where you can have something on the boundary, I think from 1954 is when that second one was proved. Okay? So from that, you'll see just a quick sketch of the fact that this thing is, the drop is symmetric, and so that leaves the exterior surface. And you remember the hockey puck, when you pulled it up and down, there was a whole family of these things. And what I'll do is just compare to the family, and here's a picture. What I do is just say, well, you have an exterior surface. Where does it touch a member of this family? Okay? And there are different cases. And you use some comparison principle type arguments. The comparison principle type arguments are due to Siegel or perhaps Conkes and Finn. Okay. So that's really what I would have to say about this exterior thing. It's quite complicated, you know, in the argument, and so I'm not sure that conveying the ideas are worth it right now. But in the last, say, 1 minute that I have, why don't I give you a small treat, okay? I would like to think that my result is sharp from a certain point of view. I believe you can remove this division hypothesis, right? I believe that that's something that can be removed, but this is a non-physical creation, right? You have to start with an unbounded bath of liquid. You know, if any one of you can find this, show me where it is, right? And so I think that in all other circumstances that you will have at least some example. Maybe it'll be different surface tensions, or maybe it'll be different gravity or something like this. Maybe you'll have different situations where there's asymmetry. And here are a couple of my numerical explorations. This top one is a double sessile drop, where I actually have different contact angles on the plate here. Okay. I assume, since we're talking about minimal surfaces here, that many of you are familiar with, say, the double bubble problem, right? These are similar to the double bubble problem, except they have gravity and they're attached to something, right? And so this is with gravity resting on a plate, and this is a double pendant drop where you have gravity and it's hanging from a plate. And so if you just took a glass and put it on top of this, that's clearly not symmetric. And at least the software tells me that this is an energy minimizer. No proofs, just ideas. So.
Any questions?
If we go way back, the third one is actually just a reflection of the second one. So this is the third one, and this is the second one. Okay? So basically it's just saying that one whole surface gets gobbled up by the plane.